Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 9th lecture on the course Marine Renewable Energy Systems offered by Department of Maritime Engineering at IIT Gandhinagar in the SwayamPrabha portal. Marine renewable energy is an essential need of the hour as we emerge towards the strongest economy in the world in advantageous position because we have a peninsular sector where we have got coastal protection on all the 3 sides of the country. So the major aim is to harness this particular natural resource what we have around us so that the energy dependence on fossil fuels can go on the declining end. In the present scenario of the fossil fuel uncertainty in terms of supply chain as well as manufacturing production systems and very high uncertainty in the cost effect, India being a developing country cannot afford to invest on the fossil fuel and can import them from any countries for that instance. So under the principle of blue economy in 2030, one has to look at what are the possible strongest provisions we have in this country to harness energy from various natural resources. If you look at that idea, then solar, wind and waves which are all natural resources available in abundance. Being a tropical country, India needs to harness on this. So, when you talk about this, policy planning and design guidelines will not alone help to do this. The engineering technology transfer is a very important aspect and facet of this improvement. Therefore, friends, the success of any policy planning, development and employment becomes truly good only when the technology is very sound enough. We are not quoting any name of the neighboring country, but the technological development of the neighboring countries are much enough, strong enough to support the policy and planning of the country. Therefore, they are able to invest on that idea and also get it materialized towards economic perspective. We are also aiming to do a similar aspect under the honorable leadership of this Prime Minister. So, the IIT Gandhinagar is taking a lead on maritime engineering in the country, and this becomes a primary agenda of this department in IIT Gandhinagar to see the capacity building on marine renewable energy systems. So, in that aspect we are looking for how one can talk about the design and development of novel systems, so that one gets an idea about the basic principles of the development of a device for wave energy harvest as a primary focus. We will also talk about the wind energy harvest in this particular course, but we will not talk anything about the solar energy harvest, which is of course discussed in other parallel course taught by my colleague at IIT Gandhinagar under Swayam Prabha. So, friends, welcome to lecture number 9, Marine and Renewable Energy Systems, Analysis, Design and Development. In lecture 9, today we are going to talk about time domain method, or let us say time domain approach towards wave energy concept, that is the design development. So, friends, you will agree and note that, and you will be able to recollect that the frequency domain approach which is usually seen as a complementary domain approach for time domain is not true in this case. Frequency domain approach essentially gives me to study and investigate the vital parameters that control the design of wave energy converters. And we know we are looking for floating wave energy converter because of its convenience in its deployment and sure shot harvest because of open sea conditions. We are looking for its stability, both hydrostatic and hydrodynamic. Hydrostatic will be ensured by ensuring the buoyancy force and its position with respect to mass center or center of gravity. Hydrodynamic force can be tested and investigated using one method which is given by Matthew. So, we call this as Matthew stability, where the dynamic tension variation can be also plotted to check whether it is stable at any instant of time. Furthermore, water depth, which is a very important concept of clean energy, is also can be handled in frequency domain approach easily, and wave approach direction will help us to design whether I am going for multi-body dynamics or a single system which can harness the maximum. Please note, friends, very importantly, in wave energy design we generally look for the fundamental frequency of the device closely in match with the peak frequency of the wave. Okay? So, this is very interesting design concept which is not applicable to any other system design at all, because if this concept is applied, we will always expect to have a failure in the system, whereas in wave energy design concept, this is the primary requirement of the design itself. So, I want to go or to obtain the maximum response of the system. System here refers to wave energy converter. So, in that aspect, for a given wave amplitude, my system amplitude, which we call as response amplitude operator, should even exceed 1. That is, my system response should be even more than the wave amplitude response. Hypothetical design. It happens, friends. I will show you in some of the designs what we did. This happens. This can be achieved by design. So, we are looking for a very unconventional, in fact, very critical system design where the response is going to be the maximum at this condition. This is true with any physical system. There is no exemption of wave energy converter on this thought process. So, in such situation, one has to ensure that the system remains stable and the power remains continuous without any interruption. So, therefore, friends, frequency domain approach is the first step what we plan towards the conceptual design and development of wave energy converter. It is not an alternate to time domain approach at all. So, therefore, in the last lecture, if you carefully notice and wind back, you will see that the absorbed power was expressed as the absorbed power, or one can say the average absorbed power. We are looking for multi-body dynamics as well. Over a wave period, over a range of wave period is given by, let us say PA, average power 1 by T over a range of period. If you know the PTO damping and the velocity of motion of the device, then one can find the average power, which otherwise said as half CPTO omega square x hat omega square, where x hat omega is the complex quantity of the response obtained from frequency domain because frequency dependent. For my convenience, I will start numbering this equation as 1 for this lecture. As I already told you, the continuous equation numbers are not given on the screen, but one can always use the relevant equations carefully as you keep on browsing the lectures in series or intermittently, right. So, now we said that the average power can be given by this equation which we have seen on the screen. We can now consider a very wide range of PTOs power takeoff systems for different damping values, okay, that is the range. A wide range of PTO must be now tested. The moment I say wide range, what is that aspect which is varying? It is the damping ratio, because x hat omega is a complex response quantity of the system obtained from the design in frequency domain approach. Okay. So, now we vary the damping of PTO and get wide range of PTOs to get the maximum power to obtain the maximum power absorption. Friends, please note, it is not the power transfer. Okay, the power transfer is different. This is power absorbed by the device. So, how much is being transferred? What have been absorbed is the efficiency of the PTO. You understand? So, friends, I will put it in a different manner here. When you look at the design of WEC, let us say WEC is a block body, wave is encountering the WEC, wave energy converter system. The system design in sense, the geometric parameters, its mass, stiffness, etc., will help us to maximize the absorbed power. Okay. So, we have already seen one important factor which you would recognize by this time, capture width ratio will help us to quantify what is the maximum power being absorbed by the device. Now, as I said in the beginning, in the previous lectures also, power absorption cannot be computed or cannot be quantified if we do not have a virtual PTO. So, we place a virtual PTO with a linearized damping and then obtain absorbed power from the so called proposed device with certain geometric properties. So, the maximization of power absorption depends upon how good is your geometric design. Okay? Now, once the PTO is then modified for a specific system availability, then how much power is given to PTO and how much it extracts out as a mechanical power is the second stage. So, the efficiency of mechanical power definitely depends on the typical design or a better design of PTO. Okay? So, second stage, the first stage is this conversion, this is the second stage of conversion. Of course, in third stage of conversion, whatever may be the mechanical power given by the PTO has to be transferred to the electric grid. So, we can say this overall efficiency, because I get a power output here, I have a power input here. So, comparing these two will give me the overall efficiency. Comparing the input power with the mechanical power will give me mechanical efficiency. Comparing the mechanical power with electric power will give me electric efficiency, and so on. Okay, you will obviously see the overall efficiency will be the products of these efficiency numbers. Okay, that is a very simple arithmetics which one can easily compute and can demonstrate this later, but that is what it is. So, friends, one has to clearly see how I am going to design the PTO now. So, we are now moving away from the design concept of the device itself to an appropriate choice of power takeoff mechanism to the device now. So, we are in the second stage. So, in the first stage, we have used frequency domain approach as an important tool to obtain, optimize, to finalize the geometric design of the device. Okay. Now, we are going to move to the second stage where I need to take an help of the time domain analysis approach to optimize the design of power takeoff systems. Okay. That is what we are looking at in this lecture and subsequently. So, now the corresponding absorbed power values for various damping on the TPO on the PTO will be estimated. So, for various PTOs, so when I say various PTOs, I am varying the PTO damping. Okay. I am not altering the system design of PTO. For the same system design of PTO, can also change the damping, tune the damping depending upon its frictional component coming from the stiffness and the hydrodynamic or the radiation component coming from the damping part. Okay, I can always do that. So, varying the PTO damping, I will get this, and I will choose the PTO for the maximum absorbed power. Okay. So, that is I can say it is an ideal PTO suitable for the device. Okay. I want to also make a statement which you will be having in your mind. PTO design is customized with respect to the device design. You cannot use any PTO for any wave energy converter. I mean, that is not a right argument here. There is an appropriateness between PTO and the WEC design. Okay. So, one has to see which method, which types of PTO will fit in what kinds of design of WEC. So, which we will discuss this in the coming lectures. Okay. Now, we are moving to the second level of our learning of designing and development of wave energy converters for renewable energy systems, where we are touching upon now the design of power takeoff mechanism. So, as I said, when you do this power takeoff mechanism calculation for different damping ratios, so when PTO is assessed for different damping ratios, then what do we get? We get an envelope, right? We get an envelope showing the power absorption characteristics. Okay, this is an envelope. So, now this power absorption characteristics will also depends on various frequencies involved in the design and various damping values. There are two variations here. One is the frequency content, of course, is there, okay, because x hat omega, it's a complex quantity, is a function of frequency itself. So, frequency dependence is always there. In addition, you have the damping dependence as well. Okay. In such cases, the output is generally expressed in terms of spectral density function. Which is referred otherwise as response spectrum, which we discussed in the previous lecture as a follow-up as well. The area of the curve under this spectrum absorb power, okay. So, the area under this curve will give the absorbed power. Okay. For different damping values of PTO. Therefore, friends, frequency domain approach provides a rough estimate of optimal PTO only. Okay. So, frequency domain approach can only provide a rough estimate of the so called optimal PTO. What is optimal PTO? Optimal PTO is the best power takeoff system which can fit in the novel wave energy converter design or the device which we developed or which we proposed. Okay. So, we are now giving only a rough estimate of optimal PTO. It cannot be the best suitable one, right. Once we said this, then how do we get the correct design of PTO? That is the question comes. Then how to get the perfect design of PTO and improved design of the device. How do we get this? Okay. So, the PTO designs, the real PTO designs or the real PTO systems and the active control systems which are used to tune the damping cannot be incorporated in frequency domain approach. Okay. Furthermore, the system assumes a linear behavior. Thinking that all linear superposition may be valid, but when there are many non-linearities present in the system, then the picture will be different. Okay. Therefore, friends, there is a necessity that we must move towards time domain modeling. This is where we stopped in the last lecture. So, I want to just make a brief overview of what we learned thoroughly in the previous one and emphasize certain points. So, the necessity of both frequency domain and time domain are understood by the viewers. Now, the time domain approach is helpful in modeling the nonlinear forces. The nonlinear forces arising from the PTO system. It can also come from the control system. It can be a nonlinear component of the potential which can all be taken care of in the time domain approach. Okay. Now, this will help us to improve the efficiency of the design and accuracy of the design. However, in linear frequency domain, all terms are generally linearized. Therefore, the response can be obtained with less computational cost and efficiency, but the accuracy will be lower. Okay. This was very clearly said by Foley in 2016 and Merigod and Ringwood in 2018. So, researchers confirmed that these statements are very important to understand the necessity of time domain model. Okay. Now, coming to this level of understanding, let us say in time domain model, all the governing equations are described or expressed as function of time. Now, if I say I am going to express all the elements of the equation of motion, then there are certain frequency dependent terms. What are they? Hydrodynamic coefficients, then response amplitude operators, then hydrostatics of the whole assembly. They are all frequency domain or dependent concepts. Okay. Now, they all will now become the building blocks for a time domain model. Okay. For example, the wave elevation or we say sea surface elevation, which is generally expressed as eta, then the velocity potential expressed as phi of an incoming monochromatic waves in time domain are generally assumed to take a sinusoidal form. Let us see this equation. So, eta of t time domain, then say eta a sin omega t minus kx cos beta minus ky sin beta plus equation number 2. Then the velocity potential in terms of spatial variation and time variation is given as eta a g by omega e k z cos omega t minus kx sin beta minus ky cos beta plus p, equation number 3. So, the sea surface elevation and the velocity potential are now expressed as a time function. Okay. Now, in this equation we talk about beta. Okay. Let us say beta is the direction of propagation of incident wave, where beta is the direction of propagation of incident wave and phi is the wave phase in the above equation. So, if I have a unidirectional wave, let us say we will not consider any wave approach angle at all. So, for an unidirectional wave, hypothetical of course, the wave elevation can be expressed as summation of different monochromatic waves with different wave elevation and frequencies, that is wave amplitude and period. Okay. Let us write this. Eta of t can be also expressed as summation of k equals 1 to, let us say, n waves, eta ak sin k waves x minus omega k waves t of k plus phi of k. Question number 3. Okay. So, in this above equation, let us say Nw is the number of frequency components which is being considered in the summation. Ak is actually the wave number. Pw is the randomly chosen phase value. Randomly chosen phase value. It can vary from 0 to 2 pi. Okay. And eta ak can be given as tau twice of S PDF of wave f of k delta f omega, where S PDF of wave is the wave spectral density function. Generated from various available spectra in the literature. For example, Pearson Moscow spectrum, John-Swab spectrum, and so on. So, all these are chosen depending upon the location of interest. Where are we designing or placing this energy converter? Okay, and Fk is the frequency content in hertz, and delta F wave is the frequency step in the above equation. Okay. So, now based on Newton's law, a typical governing equation can be developed. Balancing the time varying forces and moments and we call this initially as Cummins equation. Therefore, we in the modern term we say this is equation of motion, but actually they are in real terms Cummins equation, because they are force balance of the time varying force and moments in a given system. Okay. So, for our example, let us take a single degree WEC model. Let us see a single degree WEC model. So, we start doing a linear time domain approach. So, remember we are using a single DOF WEC model, and in that I am now employing a linear time domain approach. Now, for a linear system, the Cummins equation defines the parameters in terms of impulse function. Let us say we can recollect the pressure of the fluid from Bernoulli's equation limited to the first order. So, we know the pressure of the fluid is limited to first order as per Bernoulli equation, which we say is equal to minus rho d phi by dt. So, we estimate various forces. Okay. The entire derivation of Cummins equation is anyway available in the literature, but only the final equation, let us say, we will discuss about that, the final equation. So, the velocity potential for a small interval delta t based on Cummins theory can be given as T of t is x dot of t psi plus minus infinity to small t, t minus tau x dot of tau d tau, equation number 4. Now, the first term in this equation represents potential during delta t. Okay. The second term in this equation is the successive impulse response of the memory effect. So, now psi and c are actually normalized. Velocity potential caused by the displacement during delta t duration. Okay. So, then the hydrodynamic force which we need for our design by integrating pressure is given as Fr of t, which is Am x double dot of t plus minus infinity to t k r t minus tau x dot tau d tau, which can be said as minus double integral over the surface P r, the surface integral, equation number 5. So, from the Newton's equation including hydrostatic stiffness term, the Cummins equation for a single degree can be rewritten as mass plus added mass x double dot t, the inertia term, plus 0 to infinity k r tau x dot t minus tau d tau plus k h x of t is Fe the exciting force of T. Equation number 6. This is where the frequency domain plays an important role in estimating the radiation stiffness and applied and added mass. So, the radiation stiffness and the added mass are obtained from frequency domain approach. Okay, so we can write it here. The frequency domain approach helps to estimate the radiation stiffness and the added mass effect. Okay, so this was stated very clearly by Ogilvy in 1964. Now, I can also compare an effective method to estimate these parameters between time and frequency domain equations. So, one can also compare to estimate these parameters one can also compare the time domain and frequency domain approach to estimate these parameters, right. So, let us try to do that. So, by doing that summation and we are considering harmonic motion unit amplitude on either side of equation of motion, Am of omega can be given by Am minus 1 by omega of 0 to infinity Kr tau sin omega tau d tau. Equation number 7. Cr omega, the radiation damping, is 0 to infinity Kr tau cos omega tau d tau. By applying inverse Fourier transform to equation 8, one can obtain the time domain retardation coefficient of this value. So, from inverse Fourier transform to equation 8, one can obtain Kr of tau, which is time dependent radiation coefficient. This is actually time dependent radiation coefficient. Then I can substitute this back in equation 7. One can find the added mass term valid for all frequencies. Okay, friends, this is a very catching point, very difficult to obtain this otherwise. It's a very catching point. So, literature have lot of difference of opinion in time domain estimating added mass value. Okay. The numerical techniques are then used to estimate these parameters while solving the equation of motion and then write the hydrodynamic forces further. So, we will discuss about this in the coming lecture. So friends, in this lecture we summarize we understood the necessity of frequency domain approach for new wave energy converter design proposal. Certain parameters which are assumed to be linear damping etc. in PTO cannot be assessed and analyzed using frequency domain approach. We moved on to time domain model. We picked up a linear time domain model for single degree idealized system and we estimated how to compute the added mass term and the radiation term, which are all input to the WEC design. In the subsequent lectures, we will also expand this understanding of time domain further and see what advantage this method of analysis give us to finally come and arrive at the design of wave energy converter. Okay. So, stay connected friends. Yes, the lectures are mathematical intensive. I hope you have followed them clearly. There are references also given. I would urge to access to all these references from library, read them in detail and try to develop a good understanding of the whole base. The lectures what we give here is only about 15-20% of what your understanding should go forward. Okay, this is only an initial spark. So, you should be able to develop this further from the point where we leave at this level. Okay, thank you very much. Stay connected.